this thing right here. But this molecule is the same C4H what? 8. I didn't put the hydrogens on the other things. But they're not the same. I can't superimpose them. And that's because of the double bond. There's no free rotation. So these are two different molecules. Two different names. Now the modern way of doing this, and they still don't do it consistently, and you'll get that in organic chemistry, but they go around the carbon and then you pick the more complex groups and they use a numbering system. The old-fashioned way, which is all we're going to do, which handles simple molecules, that's all we're going to see. These are on the same side of the carbon, the two same groups, and they're on the same side of the double bond, so we call that cis. This one, they're across the double bond, so we call it trans. Okay? So now we've introduced a new type of isomerism that depends on having a double bond. And it doesn't matter whether you look at the carbons or the hydrogens, this would be cis. And this one here so they sometimes are referred to as cis-trans isomerism, the more sophisticated way. Geometric isomer, we use the word cis and trans to distinguish. And as what happened, I got too many E's in here. And I forgot my S. Anyhow, if you're using the prefixes cis and trans, we're not going to get into the numbering system. I think your book has just a little bit about how to do it, but we're not going to get that complex. And the only way you can have that type of isomerism is if you have a double bond. And notice here, since these two groups are both hydrogens, you can't have cis-trans isomerism even though there's a double bond, because this hydrogen looks the same as this hydrogen. So if I flop it around or whatever I do, I don't end up with a different molecule. There's one other one I'll talk about next time. And this has a very complex way of naming things also. We're not even going to bother naming them. We're talking about the nomenclature of those. But those are optical isomers. They're very important in modern chemistry, and we'll say more about it next time. Dr. Jones does a lot with that. Continuing on then. I think I've beaten the alkenes to death. Notice when we have alkenes, we can have geometric isomers, and we can even have a functional isomer where we went back to the saturated thing by making a cyclic structure. Anything else we can ask about this? That's about it. So the next thing I'm going to do is take away some more hydrogens, and I'm going to write alkyne. See, there's a triple bond in an alkyne. Because we took away two more hydrogens, so this is 2N minus 2. This is a linear molecule. All the atoms are in a straight line. And this is called, two-carbon chain, ethine. here's the real kicker. It has a very common name. It's the welding gas acetylene. And the kicker is, as soon as you see the word acetylene, you see ENE, and you've been studying organic nomenclature, you say what? Must have a double bond. It doesn't. When you start doing common names, you have to actually memorize the name and the structure, because each name has a particular structure that's referring to it. You can't work it out unless you've memorized it. At least with the IUPAC system, there's a certain sequence of rules. If you know the and by the way, when you're writing papers, and I know this because I put some organic molecules in my paper, if you try to use one of the common names, because that's the way it's easiest to refer to, first thing they do is kick the paper back to you and say, maybe you should look at the handbook of nomenclature and name it correctly. Because anytime you get a published article, you can't use the common names. You have to use the IUPAC name so that other people know exactly what you're talking about. Okay? So many of these things, we're doing all this experimental work with these various drug agents and things. They don't publish it because they don't want to publish the IUPAC name until they've patented a structure or something that says it like cures this disease or cures that disease. Okay. So these are the alkynes. Again, the rules work the same way. You're looking for the longest carbon chain with the triple bond. And we could have mixtures of double and triple bonds, but we're not going to do it in this class. So, but this would take precedence over this if we did that, but I'm not going to do that. What else did I want to say? This is the lowest first carbon in the triple bond should have the lower number. There is no such thing. There's no free rotation here, but it's all linear about this carbon thing. This happens to be sp hybrid for hybridization for the carbons. And triple bond, you may remember this from 1A, is made up of a sigma and 2 pi bonds. And by the way, we did that for electron dot structure for nitrogen, and it's the same rule. It's a sigma bond and a 2 pi bonds. Okay, so that's the triple bond. We've beaten hydrocarbons to death almost, except for one thing. These are alkyls, and we have multiple bonds, but what I want to do now is talk about aryls. They're referred to as aromatic compounds. I'm going to put everything in right now. Something like that. C6H6. This is a double bond, single bond, double bond, single bond. We have a resonance structure. Remember resonance from 1A? All we do is move the electrons around. I'm not going to put the hydrogens in. Now I'll move double bonds here and here. Kekulé was the German chemist who studied this. We used to use this a lot in the labs when I worked as an undergraduate. At the end of the day, we'd be cleaning glassware, and the final step would be to rinse everything out with this molecule. And then flush it down the drain. You do that now, and the EPA will throw you in jail if you don't get lung cancer first. So you won't see this in this class, you won't see it in the organic class, because this is a very common carcinogen. So we pulled that out of the lab 20 years ago. I point out, when I went to school, we would sit there, and as I said, it's very good at removing grease from the surface of the glassware. So after we clean glassware, we'd always rinse it with benzene, and we'd flush it down the drain. Before people knew any better. Some people still try to do that in industrial processes. But this is the benzene ring. It's an aromatic compound, has a very strong smell, and it has a high bond energy, so it burns with a lot of heat when you burn it. We could do these Kekula structures. You usually don't put in the hydrogens, and you usually just do this. Either this or because what happens here, these atoms are all in the same plane. Now this is made up of a sigma and a pi bond again because it's a double bond, but the pi bonds stick up above the plane of the carbon and below the plane of the carbon. And so essentially what happens is the electrons move freely through this pi bond above and below the plane. That's why they sometimes draw a structure like this. Okay? So that's benzene. That's a group of what we call aromatic compounds. I always like to mention this thing. I'm not really going to ask you about it, but okay. This is, and again you have the alternating double bond structure. Wow, I'm almost forgetting how to spell it. Naphthalene. And the reason I always have to mention this, when I started my graduate career, first I put together a high vacuum system, then I sealed a little bit of naphthalene at one end, and I put different solvents in at the other end, and I never had to touch chemicals for the next 4 years. All I did was cool things and move the chemicals around, and that's the only way to do chemistry to be safe. Okay. This is the smell you get from mothballs and things. Actually, it's dichloro, something else that we also use. But it smells the same. So that's naphthalene. And the only reason I like to mention that is that, first of all, I'm not going to ask you a question about it, but I spent 4 years working with it, doing different things, and I only touched, well, I didn't even touch it. I put it into the vacuum system with a spatula and things, and then I never had to be exposed to chemicals the rest of my career, except one time, a piece of supervisor blew up something next to my ear. That was one of the things. I also had to measure some viscosities of solvents, so I did have to touch some chemicals. But we were mostly worried about collisions of these things in non-aqueous media. Okay. This continues on. Polynuclear, this one has to be anthracene. If I put another thing down like this starts looking like, actually if I have to shift the other one around, but these are the pyrines and benzpyrines and everything. And as you add more and more things to those things, you put them on the back of the mouse, and the mouse gets huge tumors, and you say, wow, that stuff is bad. Okay? But the other thing that this looks like, when you're charcoaling food, fat turns to something that looks like that also. And that tastes really good. But so all of these molecules do different bad things, and sometimes they have good tastes and people eat them, and people say, I've been charcoaling all my life and it hasn't killed me yet. But other people said, boy, I ate a piece of charcoal meat and I have stomach cancer. Now, I don't know what they say. These are all more complex. And what's happening, if you remember that thing I showed you with the testosterone earlier, it has some of these basic structures, and you just hang different things on here, and you have different enzymes, and your body definitely needs them to survive or do something. And it isn't just testosterone, it's all the other ONE things that your body needs to manufacture things, and I guess, I don't know what's the best for you. But they all have very similar structures, and you can see why some strange molecule like this is very easy to interrupt the process that's going on in your cells and cause medical problems that different people have. Okay. So you'll have to know about benzene. That's an aromatic. Now you could say methylbenzene, but I'd mark it wrong because you always have to refer to this as toluene. If I start putting other methyl groups in here, xylenes and things like that, we're not going to get into that. So this is the only one you really have to know about. I don't think there's something else you should know about in here with these aromatics. You don't have to know about naphthalene, anthracene, pyrene, any of those things. But the benzene structure you should know about. Notice I said you could call it methylbenzene, but it would be wrong. But this would be the number 1 carbon. You go around the ring here if you have other substituents. Okay. So these are our basic aromatics, benzene, toluene. And then I'm going to get, before I do oxygens, and by the way, these are sometimes referred to as functional groups separately, but I'm going to do it as substituents. In other words, I'm going to start doing halogen substituents. When I do something like this, this is a chlorinated hydrocarbon. You hear about things like this destroying the ozone layer or whatever. So this is 2-chloropropane. So when you have the halogens, it's the stem plus O. And we saw that same sort of way of referring to these things when we were working with the complex molecules earlier this semester. So it's fluoroiodo, chloro. And now we can really boost the number of isomers. This one only has 1 isomer. The reason I wrote that, you're probably all familiar with that. That's tetrafluoroethylene. Common name is Teflon. Very inert coating for pans and things. Okay. But when I start doing two fluoro, if I put over here, it's 1 fluoro, 2 fluoro. But 2 fluorines, 2,2-difluoro, 1,2-difluoro, 1,3-difluoro, 2,2-difluoro. You can start moving them everywhere, and you get a lot of different isomers. Yes?
What would be the IUPAC name for toluene? You don't know.
This is the IUPAC name. The non-IUPAC name is methylbenzene. Yeah, so this is what you're supposed to use for this structure.
So the position of the carbon bond does not really matter?
Pardon me?
The position of the methyl group and what is it?
Right, because if I start putting something on here, now it's 1, 2, 3 chlorotoluene. Okay? You count around the circle. If I go the other way, 1, 2, 3, 4, 5 chloro, I went the wrong way. 3 chloro is low. So you always call that basic structure toluene, and then you find the substituents. That's why I wanted to go to some other things to put on there. This would be 2, 3 dichlorotoluene. Without the methyl group, then it would be 1, 2 dichlorobenzene. And then we have a common name, orthodichlorobenzene. I'll talk about that later, because I'm not going to ask you to tell me common names, but when they're talking about different reactions, they use those non-common names. Some other substituents. That's the good old nitro group. That's a TR, in case you can't read my writing. And the reason we always used to call it nitro was because in organic chemistry, in organic chemistry, it always bonds to the nitrogen. It doesn't contribute electrons from oxygen as it does when it behaves as a ligand. So this would be in organic chemistry, if I wrote it like in complex ion chemistry. Oops, carried away here. We worked from, and it's the nitride ion, there's a minus charge on there, but I was just referring you back. So we wrote it like this, it means the oxygen was donating the electron pair to the vacant orbital. Write it like this, the nitrogen is donating the electron pair. But in organic chemistry, the bond to the carbon chain is always through the nitrogen. Okay, so we always call it nitrogen. Again, through the nitrogen, it's the amino substituent. I used to put this one on, I don't know if I'll use it all anymore. As a substituent, it's cyano, but this is actually a functional group, which we don't cover in this class at all, and it's called a nitrile, N-I-T-R-I-L-E. Okay. So we can name these as separate functional groups, and in fact, this is also a functional group, except we're just going to treat it as a substituent, because I'm not going to go past functional groups where we have them based on the NH2 group in the molecule. Okay. So halogens, nitro groups, amino groups, those are the most common substituents I will stick in there to make more interesting molecules. Then I'm going to start oxidizing. But I think right now